Hello viewers, welcome back to my channel. Hope you are doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created bunch of playlists to cover various categories of the problems such as stacks, queues, trees, graphs, dynamic programming, breadth first search, binary search, depth first search, and so on. So don't forget to check them out. I have uploaded the code for this problem to GitHub repository. You can get the link from the description below this video. Let's jump into today's problem. Kth smallest element in a BST. So given a binary search tree, write a function kth smallest to find kth smallest element in it. So we are given with a binary search tree. You may assume k is always valid. 1 is less than k is less than BST's total elements. So basically we are given with a binary search tree, right? So binary search tree is has a special property. What is that? Normally the binary tree, right? So let's look at the binary tree node structure. So the node structure is given here. It has a value, it has left child, and it has a right child, right? So basically each node has a value and a left subtree and right subtree. So that is a binary tree, but binary search tree is special. So there is a additional property added to binary tree to make it a binary search tree, right? So the property is the root. So we will say there is a left, there is a value, and there is right? So instead of saying value, we will call, let's say, root. Okay, so what is that? The property is left is less than root is less than right. So in some cases they will also add less than or equal to. Okay, so in some cases they also add less than or equal to. Okay, so for our discussion, let's say we don't have this kind of equal to, but let's go with left is less than, root is less than right. So this is a BST. So it is not just at the one single node level, but that property should hold all the left subtree. So basically when we say left, right, so it's not just the left child but left subtree. Okay, and when we say right, it's right subtree. It's not just the child, right? So that's the definition of the binary search tree. So we are given with like couple of examples here, and in that we will have to find out the kth smallest, right? So normally if you are given with an array, right, so like 1 2 3 4 5, let's say this is our array. So what is the first smallest? That means the smallest element is 1, like first smallest or smallest, right? That will be 1. So what is the second smallest? It is 2. Fifth smallest, that means it's nothing but the largest element, right? Fifth smallest. So if you go fifth smallest, will be 5, right? So that's how we can come up if you have a array in a sorted manner. So as we saw, the property of binary search tree is left subtree will be less than the root and root will be less than the right subtree, right? So this will be forming a sort of a sorted order, right? So if you traverse the binary search tree through in-order traversal, right? So there is something called in-order traversal. Okay, so BST in-order traversal. Okay, so this will bring up elements in sorted order. Okay, brings up elements in sorted order. So that's the property that we are going to utilize. So we said, okay, we are given with a sorted array, finding the smallest or second smallest, third smallest is pretty easy, right? So if you are given with small array, right, so if you say kth smallest, right, kth smallest, that means if this was an array A, right, what is the kth smallest in the array A? All you need to do is array of k minus 1. That's it, is the answer. Why are you doing k minus 1? Assuming that this array is 0 indexed. Okay, array is 0 indexed, right? So that's why we are saying array of k minus 1. So since BST inorder traversal will bring up all the elements in the sorted order, so if we can get this kind of, what do you say, if we can get this kind of array from the BST, right, then we are good. What we can say is we have that many elements already present in the array, and we can say a of k minus 1 is the answer for this particular problem, right? So that is our first approach. Basically what we are doing is we will get all the elements from the BST and store it in a list. Just like this, we will store it in a list, and once we have the list available, a of k minus 1 is answer. That's it. We don't have to do anything after that. So that's our first approach. So what I'm saying is we will look at like two approaches and the optimizations in those approaches also. So put all the elements from the BST into a list through in-order traversal. So in-order traversal brings up all the elements in order, right? So sorted order. So if we have sorted order, we will be able to simply do the a of k minus 1, right? So that's what we are going to do. Since all the BST values in the list will be sorted order, let's assume there are n nodes, right? There will be n elements in the list. So we simply list of k minus 1, right? List of k minus 1 is our answer, and list is 0 indexed. That's what we talked, right? Array is 0 indexed, as opposed to I'm using a list here, right? So that is one approach, right? So let's go ahead and look at the code for this. We will come back to the second approach and look at the code for second approach in a little bit, right? So for this approach, let's go ahead and look at the code, and we will also look at the time and space, okay, for this particular thing, right? So let's go ahead and look at the code for this. So what we are saying is we do the in-order traversal, right, and put all the elements into a list. So I have this in the commented section, okay, with extra space. So we are creating a list and traverse in order with space, root, and L is passed. What is that L? L is a list. So, and finally what we are returning? L of k minus 1, right? List of k minus 1. So what we are essentially doing in in-order traversal, if node is null, then we just return. We don't have to do anything. It said k is always valid. That's why I'm blindly returning L of k minus 1. Okay, if k is not a valid one, right? So let's say if the BST has only 5 elements, but if k is 6, then we cannot directly return like this. That's the reason why if we go back to this node, right, k is always valid, we can return such that, right, L of k minus 1. So now going back to the in order with space, right? So what we are doing, go to the left subtree and go on to the left subtree until there is no subtrace at all. Once you go to that space, basically you go leftmost possible subtree as part of the in-order traversal, and then add that particular value and go traverse back with the right subtree. So with this, what we get is the list will be filled up. So for example, right, so if we go through this 3, 1, 4 to the example 1, right? So the list will have, L will have what? So we go from here and go traverse left. So we go traverse left. There is no left here, right? So what we are doing, add tn dot value. So we will add 1 to our list. So 1 is added, and then we go onto the right subtree, right? So for 1 there is right subtree 2. So for 2 it will go left subtree and right subtree. Those are two nulls, right? So now after that it will add 2 to the list. Okay, so 2 is added. So now it comes back up. So since the left subtree is already passed and passed through, what we are going to add the current node. So that is 3, and traverse the right subtree, right? That is with the right. That is 4. So 4 doesn't have left subtree or right subtree. We just add 4 into the list, right? So that's how we are able to go through this recursive method, right? So now what is k? K is 1. So what we said, k minus 1, that's what we are going to say, right? So this list of, so the answer is L of k minus 1. K is 1. 1 minus 1 is 0, right? LF 0. That's what we are going to. What is LF 0? 1. So this is what we are going to return. So what is the time complexity for this? Basically, we are traversing through all the nodes, right? So if there are n nodes, that's what we said, right? So the time complexity will be order of n, where n is number of nodes in BST, right? And what is the space that we are using? Since there are n nodes, there will be n in this list, right? N integers in this list. So we will say the space is also order of n, where n is the number of nodes in the binary tree. So our first approach is taking the order of n time and order of n space. So we could actually make a betterment with this. So basically what we are going to say is we can improve this time complexity and space complexity with this method itself by keeping track of k elements, right? All we need is only k elements, right? We don't have to actually need all the n elements to find out the kth element. How many elements we actually need? Only k elements. So we can make a small improvement so that it will be doing only the k elements collection and k element lookup, right? So in that case, what we will say is that improvement, the optimization, right? So optimization. I don't have the code here for that yet, but you can probably get that very easily. Optimization. So what we can do the optimization? So order of time will still be order of k, right? And space also order of k. So we don't have to go through all the n elements per se, right? So we have reduced the time complexity with optimization to order of k, and space also complexity to order of k. So there is a little bit of code that need to be done for this. So let's go ahead and look at the second approach, what we are going to do, right? So let me close this and come back to this. Okay. So our second approach is we will use the same in-order traversal, right? So we will use a similar in-order traversal and pass k also to it. So instead of using any space, so here we are going to bring down the space to constant space for this second approach. In the first approach, the space was order of n. When you optimize, the space became order of k. But in the second approach, we will be doing the space to order of 1. So it will be constant space. That's what we are saying. So what we are essentially passing is, for the recursive function where we are doing in order traversal, right? We will pass the k as and when we see an element, that the value, right? So the value as part of this one tree node, we will decrement the k as and when k becomes 0, right? The current element is the answer. The current node is the answer for kth smallest element, right? So we keep recording the k is equal to 0, and the recorded element is the answer for kth smallest. So the recursion for the in-order traversal will do the processing of the left subtree first and the current node and then right subtree. That is how we said it is going to give you the elements in increasing order, basically the sorted order, right? So let's go ahead and look at the code for the second approach. So the second approach, what I'm saying is, you say traverse in order, which will take two parameters now, the tree node and the k, the value of k, right? So if the tree node is null, we just return, we don't have to do anything. But otherwise, we will have to go to the left subtree with the k passed as reference, right? So once we reach to the leftmost subtree, right? So leftmost subtree is, if in this case, the example 1 case, we will reach only until 1. But in example 2 case, we will reach until 5, 3, 2, 1. So 4 levels basically. But for example 1 case, we just reach 2 levels, right? Likewise. So traverse in order, we go on to the left subtree and left subtree and left subtree and so on. So once we encounter the leaf nodes, right, then we will decrement k, and if k is equal to 0, we will record that kth smallest as the current node's value and then return from then and there itself. You don't have to process all other nodes at all. Once we find the kth smallest, just return from there, that's it. But if you haven't found the k is not equal to 0 yet, then you will have to go to the write subtree and process further, right? So whenever we end this, right, when k is equal to 0, it will end and kth smallest will be recorded and returned. So we call travels in order from the main function with root and reference with k value. Whatever the kth smallest we have accumulated as part of this if loop, right, we will return that. So basically this will improve the time complexity to order of k. So since we are going through the recursion levels, right, here what we can say is the recursion levels are given as in terms of the levels of the binary tree. So we will say how many recursion levels we are passing through. It will be in the order of the levels of the binary tree, right? So since we are doing this recursion through the levels of the binary tree, right? So the traverse in order to the left, it is going through all the H levels, let's say, all the H levels to identify that one. So the time complexity for this, in other words, we could say is order of H levels. And what is the space complexity that is being used for this? So the time, let's record the time. So order of H we will say. And what is the space? Are we using any extra space? We are not, right? So we are only using one space for the integer to keep track of the kth smallest, right? So we will say the space complexity is order of 1. So between these two approaches, the second approach, we were able to improve the time complexity and space complexity quite a bit, right? So if you have any further questions, please post them in the comment section below this video. I have posted this code to the GitHub repository in a couple of languages, C# and Java. You can find the link in description below this video. If you haven't subscribed to my channel yet, please go ahead and subscribe and also share among your friends. Please click on the bell icon so that you will be notified about my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe. Goodbye.